Hello AP Physics students, it's Mr. Kennedy here. This video is going to be your last video of new material in the whole year. So this video marks the end of the course. And while I'll have some review videos up, this is the last thing. And it's going to be a short video too, so let's dive into it. I hope everybody's doing great. Hope everybody's staying safe and healthy. But here's our last one. This is the last day of new material. And we're going to talk about are Maxwell's equations. Now, this again is one of those topics like I talked about with AC current. We're right at the edge of what would be the next big thing that comes in where the course just ends. So you'd see these equations much more prominently in the next course you would take. But the number one thing here is to identify what these equations are, know how to use them, and in most cases you already know how to use them, and then what their meaning is. But in Maxwell's equations, the first thing we jump into is what are they? Number one, what is the first Maxwell equation? The integral of E dot dA is equal to the sum of all charge over epsilon naught. In other words, Gauss's law. The first Maxwell equation is Gauss's law. It tells you that if you integrate the electric field over some surface, that is equal to the electric flux, which is also the same as the charge enclosed inside that surface divided by epsilon naught. Both sides of those are the flux. Number two, probably the one that they ask you about the most, is this. It's the integral of B dot dA equals 0. Now this is specifically for a closed surface. In other words, a surface that closes on itself. And what this says is if we take a magnet and we have a north pole and a south pole, and you draw magnetic field lines through here, that if you try to have a closed surface, any closed surface, and let's say I'll just draw it here, that the number of lines that enter and leave must be the same. Whatever goes into that surface, whatever comes out of that surface, that's a completely closed on itself surface, has to be 0. The ramification of this is that you are not allowed to have a magnetic monopole. That there's no north pole sitting by itself, no south pole sitting by itself. That's very different than what you see in electricity. In electricity, you can have charges that are by themselves, a positive charge or a negative charge. But in magnetism, you're not allowed to have that. That there's a north pole, there has to be a south pole. There must be that corresponding part. So no matter what happens, this means that there's no monopoles. So the first one was Gauss's law. The next one, which is really called Gauss's law for magnetism, really means there's no monopoles. So there's our first two. The next one, number 3, this says that the path integral of the magnetic field over a path is mu naught times the current enclosed. This is Ampere's law. And again, it's the magnetic field over a path. Whatever is inside that path in terms of currents must be equal to this path integral. So it allows you to find magnetic fields pretty easily. And the last one, which is the one we just did and focused on in this unit, was Faraday's law. So it says the voltage, although they typically call it EMF, is going to be negative N times the derivative of the magnetic flux, which I like to write out as integral of B dot dA. Now we have to be a little bit careful here because I thought the integral of B dot dA here was 0. Well, this is for a closed surface, anything that's completely closed on itself. This can be an open surface, so just like a ring of, let's say a wire or something like that. So this is open and this is closed on itself. So you can actually have a magnetic flux through that surface there, where here you really can't. And Maxwell's equations are really a synthesis of everything that happened within electricity and magnetism. You've got Gauss's law for magnetism, Ampere's law, and then Faraday's law. And what Maxwell did was put them all together and show how they were connected. And again, that's really part of the next course that comes up. But you should know flat out what Maxwell's equations are and what their meaning is. But specifically focus on this one because that's the one they most likely ask you about, because these are usually involved in calculations. So knowing what Maxwell's equations are is pretty big. But let's take a little focus on this last one here. The last one, this is voltage. Again, they call it EMF regularly, but it's really voltage. So, but we already know what voltage is. We had a definition of voltage before. And that actually ties every single thing together here kind of nicely. We knew that voltage was negative the integral of E dot dr. The electric field over some distance there, that is the voltage. But by Faraday's law, the voltage is also negative N times the derivative of the magnetic flux. And what you can see by really putting these two things together is that electricity and magnetism are completely linked together. They are related. You start changing the magnetic flux, you get electricity. You start messing with electricity, you get magnetism. These two things are really two sides of the same coin. And again, later on, you're going to actually just treat them as one field. You'll treat them as one big field called the H field. So, but that's coming up later. But notice that within these equations, there was never anything about wires. There's nothing that says you have to have a wire. So, for instance, one of the things that can happen is you can induce current even by just having a piece of metal. Let's say you take a piece of metal and you move it inside a magnetic field, like move it in the Earth's magnetic field, a current will be generated in that. Let's say you take a magnet and drop it through a tube, a current will be generated in the tube. But one of the coolest things you can actually do with this is if you take like a piece of metal and you bring it, let's say like in a conveyor belt, let's say there's a piece of metal and all kinds of other pieces of recycling and all kinds of other things. If you bring it over a magnet, that piece of metal will become magnetized because it'll have a current that runs through it. It's called an eddy current. The eddy currents that happen will allow things that are not necessarily magnetic to become temporally magnetic because you pass them by a magnetic field because they have currents that flow through them. So if you were going to take a little conveyor belt here, and you have all kinds of refuse and recycling and other things, and you want to separate out what is the metal pieces from, let's say, just old food and other things. What will happen is you pass it over a magnet. When it passes over the magnet, it becomes temporarily magnetized, and you can pull those pieces out and leave the rest in. And actually, they have some complicated versions for doing this by actually magnetizing other pieces as well. But the whole idea is that you can actually temporarily magnetize metal even when it's not metal. So take a piece of copper, you run it by a magnetic field, it becomes temporarily magnetized because small eddy currents are running in there. There's little currents flowing inside the piece of metal. We got a piece of metal here. You'll get little currents that flowing because you don't necessarily need a wire to make that happen. So again, this never implies a wire. It implies that a changing magnetic field, changing magnetic flux will produce a voltage and possibly a current inside of things, even without that wire being present. So a neat way to sort out material as well as one example, but it can happen in anything. You even take a piece of metal and wave it in a magnetic field. It'll start to happen as we showed before. All right, everybody, that is the last thing in the course. That's it. So you can start on worksheet number 4. It's really short. And then after that, it's really time to get into reviewing if you haven't started already, and hopefully you've already started. the more review you do, the better. All right, everybody. Feel free to email me with any questions, and I will hopefully hear from you soon.